In the vast cathedral of the cosmos, a silence, colder than Earth's frost, endures untouched by machines. Scientists have cooled atoms to near absolute zero, yet physics itself blocks the final step. Absolute zero is not just a temperature. It's a forbidden frontier where motion ceases and entropy stops. This coldest point exists not in space, but in realities, eternal, unreachable. It hums in quantum equations, a whisper of probabilities. Approaching it brings paradox. Particles lose position, time falters. Not a destination, but a boundary etched into existence, beyond which our understanding trembles and the universe guards its deepest secrets. In the hush between breaths, in the stillness before dawn, there exists a silence, not of sound, but of motion. A quiet so profound it cannot be hurriedly approached. It is the edge of absolute cold, a frontier first glimpsed not in the depths of space, but in the flickering gaslight of 19th century laboratories. Here, amid chalk-dusted blackboards and glass vessels humming with volatile vapors, scientists began to map a new dimension, not of space, not of time, but of temperature. They were not chasing warmth, nor light, nor even power. They were hunting for stillness, for the point at which all movement ceases, the zero of energy, the end of heat. It began with numbers, with equations scribbled in ink that would ripple through centuries. In 1848, William Thomson later enshrined as Lord Kelvin stood at the precipice of a revelation. While others measured hot and cold as relative sensations, Kelvin saw deeper. He looked into the behavior of gases, their expansion when heated, contraction when cooled, and asked a radical question. What if this trend continued? If a gas shrinks by a fixed fraction with every degree drop, what happens when that shrinkage reaches its limit? When volume approaches nothing? From this simple extrapolation emerged a new scale, one anchored not to boiling water or freezing brine, but to an immutable anchor, absolute zero. At precisely 273.15 degrees Celsius, Kelvin calculated, molecular motion must theoretically halt. No more jostling atoms, no more vibrating bonds, only perfect rest. This was not merely a number. It was a prophecy written in mathematics, a prediction that beneath the familiar world of warmth and chill lay a fundamental flora bottom to cold itself, and yet no one had ever seen it. No instrument could touch it. It existed only in theory, a ghost haunting the edges of thermodynamics. To understand how this idea took root, one must return to the early experiments that gave birth to the science of heat. Long before quantum mechanics or relativity, before even the concept of the atom was widely accepted, pioneers like Robert Boyle, Joseph Louis Galou, and Jacques Charles probed the invisible dance between pressure, volume, and temperature. Their tools were humble: glass tubes sealed at one end, mercury traps, water baths, but their insights were monumental. Boyle's law revealed that compressing a gas increases its pressure, implying that air was not continuous, but made of discrete particles colliding against walls. Gay-Lussac showed that gases expand uniformly with heat, suggesting a deep symmetry in nature. Charles quietly noted something even more profound. Cool a gas enough, and its volume diminishes in a straight line, linear, predictable, relentless. Plot that line backward. and it vanishes into nothingness at the same mysterious temperature Kelvin would later name. This convergence was no accident. It hinted at a universal truth. Temperature is motion, not just metaphorically, but literally. Heat is not a substance, as once believed in the discredited caloric theory. It is kinetic energy, the frantic trembling of molecules, the jitter of atoms in a lattice, the ceaseless collisions in a gas. Cold, then, is not a presence, it is an absence, a subtraction, a slowing down. But can motion ever truly stop? That question tormented James Prescott Joule, a Manchester brewer turned physicist whose meticulous experiments in the 1840s forged the link between mechanical work and thermal energy. By stirring water with paddles and measuring the rise in temperature, Joule demonstrated that energy transforms but never disappears. His findings laid the foundation for Third Law of Thermodynamics. Energy is conserved. Yet, within this conservation lurked a paradox. If energy cannot be destroyed, why does heat always flow from hot to cold? Why can't a cup of coffee spontaneously reheat itself by drawing energy from the cooler room? Enter Rudolf Clausius, the German physicist who, in 1865, gave the universe its most melancholic law. He named entropy, measure of disorder, of irreversibility. Every transfer of heat increases entropy. Every process leaks energy into chaos. Time, he realized, has a direction, and that direction points toward equilibrium, a lukewarm sameness, where no gradients remain, no work can be done. The universe, left to itself, trends toward stillness. Absolute zero became peace in this framework, not just a temperature, but a final state, the ultimate equilibrium, the end of change. Yet scientists are not philosophers, they are experimenters. And so, while theorists pondered the meaning of zero, others sought to touch it. Michael Faraday, the self-taught genius of electromagnetic induction, turned his attention to gases in the 1820s. Could they be liquefied? Under pressure, many substances transition from gas to liquid steam, to water, for instance. But certain gases, like oxygen, nitrogen, and hydrogen, resisted all attempts. They seemed immune to condensation, earning the label permanent gases. Faraday refused to believe it. Through brute force-sealing gases in strong iron tubes and chilling them with evaporating liquids, he succeeded in liquefying chlorine, ammonia, and carbon dioxide. But the truly elusive gases remained gaseous. His failure was instructive. It suggested a threshold. Perhaps extreme cold, not just pressure, was required. Perhaps these gases could only become liquid near the very edge of cold. The race was on. Across Europe, physicists devised ever more cunning methods to plunge temperatures lower. Thaddeus Lowe used sulfuric acid to absorb moisture and cool air. Raoul Pictet employed cascading evaporation, letting one gas boil to chill another, which then chilled a third. In 1877, both Louis-Paul Cailletet and Raoul Pictet independently reported the liquefaction of oxygen, glowing pale blue in fragile glass vials. Nitrogen followed soon after. The permanent gases were tamed, but helium, lightest of all noble gases, most resistant to interaction, remained defiant. Enter Heike Kamerlingons, a Dutch physicist of quiet intensity and meticulous precision, appointed professor at Leiden University in He built a cryogenic laboratory unlike any other, a temple to low temperatures, equipped with advanced vacuum pumps, precision gauges, and a commitment to systematic measurement. His motto, Doormeten tot weten, through measurement to knowledge. Ons understood that reaching colder realms required more than brute cooling. It demanded control, stability, patience. He improved liquefaction techniques, pioneered the use of regenerative cooling, where expanding gas chills itself in a feedback loop, and established industrial-scale production of liquid hydrogen boiling at just 20 Kelvin minus 253 degrees Celsius by 1898. Still, helium eluded him. Helium, discovered in the spectrum of the sun decades earlier, was rare on Earth, found only in trace amounts in natural gas deposits. Its atoms were tiny, weakly interacting, and incredibly fast-moving due to their low mass. To slow them down enough to form a liquid, Ons would need to breach the 4 Kelvin barrier realm so cold it bordered on the impossible. For years, he refined his apparatus. Vacuum flasks, interlocking coils, helium compressed, pre-cooled with liquid hydrogen, then allowed to expand suddenly, siphoning energy from itself. The laboratory at Leiden became a cathedral of cold, humming with compressors, veiled in frost. Then, on July 10th, 1908, in a dimly lit room, thick with the scent of ozone and chilled metal, it happened. A glass tube, wrapped in silvered insulation, revealed a faint shimmer. A drop, then another, clear, weightless, rising slightly against gravity's pull. Liquid helium finally conquered the temperature, 4.2 Kelvin. The achievement was monumental. For the first time, humanity had breached the 4 Kelvin threshold. The last gas had fallen. The door to the ultra-cold was open, but Ons did not stop. He probed deeper. What happened when matter approached absolute zero? Did it behave differently? In 1911, while measuring the electrical resistance of mercury cooled in liquid helium, he observed something inexplicable. At exactly 4.19 Kelvin, the resistance vanished completely. Electrons flowed without friction, without loss, without heat. The wire became a perfect conductor. He called it superconductivity. It was the first hint that the ultra-cold was not just a colder version of the familiar world, but a different world entirely. A place where classical physics faltered, and stranger laws took hold around the same time. Piotr Kapitsa in Cambridge and John Allen in Leiden would discover that liquid helium below 2.17 Kelvin could climb walls, flow through impossibly narrow channels, and conduct heat faster than any known material. It had become a superfluid, quantum liquid that defied viscosity, defied gravity, defied intuition. These phenomena were not errors, not anomalies. They were signals, whispers from a hidden layer of reality, where particles lose their individuality, where waves dominate matter, where the rules of the everyday dissolve. And yet, despite these triumphs, a deeper truth loomed. No matter how ingenious the method, no matter how powerful the apparatus, absolute zero remained unreachable. Scientists had come close within billionths of a Kelvin in modern dilution refrigerators, but never arrived. The closer they got, the harder it became. Cooling requires removing energy, but as temperature drops, the very definition of temperature becomes slippery. At near zero, thermal energy is so sparse that extracting the last traces demands infinite effort. In 1912, Walther Nernst proposed what would later be formalized as the Third Law of Thermodynamics. It is impossible to reach absolute zero in a finite number of steps. Not impractical, not difficult, impossible, like chasing a horizon. The target recedes as you approach. This was not a limitation of engineering. It was a law of nature. Why? Because at the quantum level, stillness is forbidden. Werner Heisenberg's uncertainty principle, formulated in 1927, declared that particles cannot have both precise position and precise momentum. The more you confine a particle, the more it jitters. Even at the lowest possible energy, systems retain zero-point energy, a faint hum of motion that cannot be silenced. Electrons continue to orbit. Atoms continue to vibrate. Space itself seethes with quantum fluctuations. Absolute zero, then, is not just unattainably a mathematical ideal divorced from physical reality. There is no such thing as perfect rest. The universe refuses stillness, and so the quest for cold transformed. It was no longer about reaching zero, but about exploring the strange terrain just above it, a realm where quantum effects dominate, where matter behaves as waves, where entire collections of atoms synchronize into single quantum states. This is the domain of Bose-Einstein condensates, predicted in 1924, achieved only in 1995. When rubidium atoms cooled to nanokelvin temperatures merged into a single macroscopic wave function, a superatom visible under a microscope. It is the realm of quantum entanglement, where particles separated by distance share a fate, acting as one entity, a phenomenon now studied in ultra-cold trapped ions. It is the frontier where time seems to stretch, where chemical reactions occur at glacial speeds, where new phases of matter emerge like time crystals, structures that oscillate forever without energy input, existing in a perpetual loop of motion at near zero. All of this sprang from a simple question: how cold can it get? And yet, the deeper implication lingers. If absolute zero cannot be reached, if the universe insists on motion, on fluctuation, on energy even in its most frugal form, then perhaps cold is not the opposite of heat, but its shadow, a counterpart, a necessary half of a cosmic balance. Temperature, it turns out, is not just a property of matter. It is woven into the fabric of space-time. Consider the vacuum of deep space, the coldest natural environment known, the cosmic microwave background, the afterglow of the Big Bang, radiates at 2.7 Kelvin. This is not arbitrary. It is the temperature of the universe itself, stretched thin by 13.8 billion years of expansion. Even in the void, there is warmth, residual, faint, inescapable, only in artificial isolation, within magnetic traps, laser-cooled chambers, shielded from starlight and cosmic rays we approach the nanokelvin regime, and even then, we do not touch zero. Perhaps that is the lesson. Cold is not an end. It is a threshold, a portal. Every attempt to cool matter is also an act of revelation. Strip away thermal noise, and the quantum world emerges strange, coherent, interconnected. The chaos of heat obscures the underlying order. Only in stillness can we perceive the symphony beneath. Kelvin in naming the scale. could not have foreseen superconductivity, or Bose-Einstein condensates, or the quantum vacuum's restless energy. He saw only the limit, but the story is not about the limit. It is about what lies just beyond our grasp. The pursuit of cold has always been a pursuit of understanding, of peeling back layers of noise to see the structure beneath. From Joule's paddle wheel to On's Dewar flask, from Clausius equations to the quantum traps of today, the journey downward has been a journey inward. As we stand at the edge of the ultra-cold, we face a mystery older than science itself. What does it mean for something to be cold? Is it the absence of motion, or the emergence of a deeper kind of order? Is it the death of energy, or its most subtle, persistent form? We may never reach zero, but in trying, we have discovered a universe far stranger than we imagined. One where cold is not emptiness, but fullness, where silence speaks and stillness dances. There is a place in the universe where time slows, light dims, and motion falters, where atoms, those tireless dancers of matter, begin to stumble, their steps growing sluggish, hesitant. A place so cold that breath would freeze before it could form, where even the hum of electrons softens into silence. It lies not in the shadow of a distant star or the hollows of interstellar space, but at the very edge of physical law, absolute zero, 0 Kelvin, 273.15 degrees Celsius, the theoretical end of temperature. But as scientists pressed closer, they encountered something unexpected. Not merely technical difficulty, not engineering limits, something far more profound, a wall, not made of steel or stone, but of principle. A boundary inscribed into the fabric of reality itself. No matter how advanced the cryostat, how perfect the vacuum, how refined the cooling technique, this threshold refuses passage. It recedes like a mirage, always just out of reach. This is not failure, it is revelation. The deeper truth begins with a shift in perception, one so fundamental it altered the course of science. For centuries, heat was thought to be a fluid, an invisible substance, caloric, that flowed from hot to cold. Cold, then, was simply its absence. But by the mid-1800s, this illusion shattered. Through the meticulous work of Joule, Clausius, and Maxwell, a new understanding emerged. Temperature is motion, specifically the average kinetic energy of atoms and molecules. Warm objects jitter furiously, cold ones tremble faintly. To cool something is not to remove a substance, but to slow down its constituents, to quiet the internal storm. And so, absolute zero became redefined. Not just the absence of heat, but the cessation of all thermal motion, a state in which every atom stands perfectly still. No vibration, no rotation, no translation. Total rest, a logical conclusion, and one that, upon closer inspection, cannot exist. In 1912, German physicist Walther Nernst proposed a radical corollary to the laws of thermodynamics. After years of studying chemical reactions at low temperatures, he observed a pattern as systems approached absolute zero. Their entropy, the measure of disorder, tended toward a constant minimum. More strikingly, reaching that minimum required infinite effort. Cooling became exponentially harder the closer one got. It was as if nature erected a barrier, not through force, but through impossibility. This insight would crystallize into what is now known as Third Law of Thermodynamics. It is impossible to reduce any system to absolute zero in a finite number of operations. Unlike the first two laws, conservation of energy, the increase of entropy. The third law speaks not of behavior, but of limitation. It defines a horizon beyond which science cannot go, not because we lack tools, but because the universe will not allow it. For decades, physicists treated this as a practical constraint in engineering hurdle. Surely, with better insulation, stronger magnetic fields, more sophisticated refrigeration cycles, humanity might one day breach the final degree. Perhaps future civilizations, harnessing energies we cannot yet imagine, could freeze matter into perfect stillness. But then came quantum mechanics, and with it, the most unsettling discovery of all, even at absolute zero. Nothing is truly at rest. In 1927, Werner Heisenberg unveiled his uncertainty principle, a cornerstone of quantum theory. It states, simply, that certain pairs of physical properties, like position and momentum, the more you know about one, the less you can know about the other. This is not a flaw in measurement. It is a feature of reality applied to temperature. This principle delivers a fatal blow to the classical notion of absolute zero. If an atom were to come to complete rest, we would know both its exact position, fixed, and exact momentum, zero. That violates quantum law. Therefore, perfect stillness is forbidden, even in the deepest cold. Even in the emptiest vacuum, particles retain residual motion. This is zero point energy, the lowest possible energy state of a quantum system, mandated not by heat, but by wave-particle duality. In quantum field theory, every point in space behaves like a tiny harmonic oscillator humming with irreducible fluctuations. These are not theoretical abstractions. They have measurable effects. One such effect is the Casimir force, predicted in 1948 and experimentally confirmed in 1997. When two uncharged metal plates are placed extremely close together in a vacuum, they are gently pushed toward each other. Why? Because between them, only certain wavelengths of quantum fluctuations can exist. Outside, all wavelengths persist. The imbalance creates pressure, invisible tide arising from nothingness itself. This force, though minuscule, is real, and it is powered by zero-point energy. Another is spontaneous emission, where atoms in excited states decay without external influence, triggered by vacuum fluctuations. Orlum shift, a tiny change in hydrogen's energy levels caused by interaction with the quantum vacuum. These phenomena confirm a startling truth. Empty space is not empty. It is alive with potential, vibrating with unseen energy. Thus, absolute zero becomes a paradox, a mathematical ideal with no physical counterpart. Even if all thermal energy could be removed, and it cannot, quantum mechanics ensures that motion persists. Atoms vibrate, electrons orbit, fields fluctuate. The universe refuses to fall silent. Albert Einstein, who had already dismantled classical notions of space and time, played a crucial role in this unfolding mystery. His 1905 paper on the photoelectric effect introduced the idea that energy comes in discrete packets. Light, once thought to be a continuous wave, behaved like particles. Max Planck, whose earlier work on blackbody radiation first hinted at quantization, had reluctantly proposed that energy exchange occurs in fixed units. Einstein embraced this radical idea, showing that energy is not infinitely divisible. This has profound implications for cooling. To remove energy from a system, you must extract it in discrete amounts. As temperature drops, the available energy quanta becomes smaller and smaller. Eventually, the gaps between energy levels grow larger than the remaining thermal energy. There is no fraction of a quantum to remove. The system becomes trapped in its ground state not because it has reached zero, but because it cannot shed the last remnants of energy in a way consistent with quantum rules. In essence, cooling is quantized too. You cannot slide smoothly into absolute zero. You approach it in steps, each step requiring exponentially more precision, more isolation, more time. And at the end, you do not arrive. You plateau, hovering just above the abyss, forever separated from true zero by a gap that cannot be crossed. By the 1930s, the scientific community began to accept the unthinkable. Absolute zero is not a destination. It is a limit knot, unlike the speed of light in relativity. Just as no object with mass can reach light speed, no system can ever achieve 0 Kelvin. Both are asymptotes, edges of possibility defined by deeper symmetries of nature. Yet the shock ran deeper than physics. It was philosophical for centuries. Science had been built on the assumption that, given enough knowledge and technology, any frontier could be crossed. The unknown was merely the not yet known. But here was a boundary that no advancement, no genius, no future machine could overcome, not due to ignorance, but because of understanding. To reach absolute zero would require violating the uncertainty principle, or erasing quantum fluctuations, or suspending the laws of electromagnetism. In other words, rewriting reality. Cold, once seen as a simple absence, had become a mirror reflecting the structure of the cosmos. Its unreachable floor revealed that the universe is not mechanical, deterministic, and silent but dynamic, probabilistic, and humming with latent activity. And so, a new question arose. What does it mean for science to encounter a limit it cannot surpass? Not a technological wall, not a financial constraint, but a principle, a rule written into existence itself. Einstein himself grappled with such boundaries. His theories of relativity redefined simultaneity, mass, and gravity not by expanding control over nature, but by revealing the conditions under which control fails: event horizons, light cones, cosmic speed limits. He understood that true wisdom lies not in conquering limits, but in recognizing them. In this light, the third law of thermodynamics takes on a solemn dignity. It is not a defeat. It is a statement of cosmic consistency. Consider the coldest known natural environment, the Boomerang Nebula, located 5,000 light-years away. Expanding gas from a dying star has cooled to just 1 Kelvin, colder than the cosmic microwave background. Yet even here, atoms move. Photons from distant galaxies trickle in. The nebula radiates faintly, slowly warming. Perfect cold does not exist in nature. The coldest temperatures ever achieved are human-made. In laboratories using laser cooling and evaporative techniques, physicists have reached 38 picokelvin. That's 0.1038 K. Recorded in a 2021 experiment aboard the International Space Station with rubidium atoms in microgravity. At such extremes, time dilates perceptibly due to relativistic effects. Atomic vibrations stretch into seconds. Quantum waves expand to macroscopic sizes, and yet, still not zero. Each new record feels less like progress and more like reverence. A ritual of approach, not arrival. Modern experiments in ultracold physics no longer aim to break the zero barrier. Instead, they study what happens near it. In these regimes, matter undergoes astonishing transformations. Bose-Einstein condensates form when clouds of bosonic atoms collapse into a single quantum state, behaving as one giant wave. Superfluid helium flows without viscosity, climbing walls in defiance of gravity. Superconductors carry current indefinitely, their electrons paired into coherent entities that ignore resistance. These are not just curiosities, they are manifestations of quantum coherence. Order emerging from near stillness. The chaos of thermal noise, stripped away, reveals an underlying unity. Particles lose individual identity. Boundaries blur. The microscopic becomes visible. In this sense, the impossibility of absolute zero may be a gift. If perfect stillness were achievable, the quantum world might remain hidden. Thermal motion masks coherence. Heat disrupts entanglement. Only by approaching, but never touching, zero can we glimpse the delicate architecture beneath. There is a parallel in cosmology. The Hubble Deep Field images, capturing galaxies billions of light years away, required long exposures in near perfect darkness. Too much light, too much noise, and the faint signals vanish. So too in cryogenics, to see the quantum universe clearly, everything must be slowed, quieted, cooled, but never silenced. Perhaps this is the deeper lesson: the universe does not permit silence. From the quantum foam of space-time to the cosmic web of galaxies. From the spin of an electron to the expansion of the void, there is always motion, always change, always energy in some form. Even in the far future, when stars burn out and black holes evaporate via Hawking radiation, the universe will not reach absolute zero. According to current models, the eventual temperature of the cosmos will asymptote toward a non-zero value, perhaps influenced by dark energy or residual vacuum fluctuations. True equilibrium may never occur. Absolute zero, then, is not just physically unreachable. It may be cosmologically meaningless, a concept useful for calculation, but absent from reality. And yet, humanity continues to chase it, not to violate the laws, but to honor them. Each attempt to cool a sample, to isolate a system, to push another decimal place lower, is an act of listening, an effort to hear the faintest whisper of nature's inner voice. In the lab, scientists do not fight against the third law, they dance with it. They exploit its constraints, using magnetic traps, optical lattices, and feedback loops to manipulate atoms at the edge of stillness. In doing so, they uncover new states of matter, test quantum gravity models, simulate exotic phases like those in neutron stars, and explore the foundations of information and entropy. The forbidden wall, it turns out, is not a dead end. It is a threshold. And standing before it, scientists confront a truth older than thermodynamics. To understand a system, you must understand its limits. Just as death gives meaning to life, so does impossibility give shape to possibility. Without the unattainable, the attainable would have no direction. The pursuit of cold, once thought to be a conquest of nature, has become a meditation on its boundaries. In the silence between atomic vibrations, in the hum of the quantum vacuum, In the asymptotic approach to zero, there is a kind of awe, not the awe of mastery, but of humility. For in seeking to freeze the universe, we discovered that it cannot be stilled, that even at its coldest, it pulses with potential. That motion is not an accident of energy. It is woven into being, and perhaps, just perhaps, the universe was never meant to stop, because in stillness there is no time, no change, no story. Only in the faint tremor of a helium atom at 0.1001 Kelvin, trembling not from heat, but from the quantum mandate to exist, does the cosmos affirm itself. It is not warm, it is not cold, it is alive. In the silence of a shielded chamber, their motion, once frantic, has been tamed to a crawl. Each atom moves at less than a millimeter per second, as if wading through time itself. The temperature, 100 billionths of a Kelvin above absolute zero. Here, at the edge of stillness, the universe reveals a face rarely seen, a realm where matter ceases to behave like particles and begins to act like waves, where individuality dissolves into unity, where quantum laws dominate every breathless moment. This is not nature's doing, it is human invention. A machine, fragile, humming with precision, has brought them here, not by brute force, but by cunning, by exploiting the subtle rules of quantum mechanics and thermodynamics to do what seems impossible, to chase cold beyond all reason, to approach a limit that cannot be reached, yet must be pursued. The 20th century became a quiet war against heat, not the fiery heat of stars or engines, but the insidious warmth within matter itself, the atomic jostling that obscures the quantum world. Scientists realized that to see deeper into the fabric of reality, they had to go colder, much colder. And so began an engineering odyssey, one defined not by speed or power, but by stillness. The first breakthrough came not with lasers or magnets, but with clever chemistry, Fedolution, refrigerator. Invented in the 1960s, it operates on a principle as elegant as it is counterintuitive. It uses the mixing of two isotopes of helium-3 and helium-4 at temperatures near 0.01 K to produce continuous cooling. When helium-3 dissolves into superfluid helium-4, it absorbs energy from its surroundings, effectively siphoning heat out of the system, like salt melting ice, but at temperatures colder than deep space. These devices can sustain temperatures below 0.002 Kelvin for weeks, even months. They became the workhorses of low-temperature physics, enabling discoveries in superconductivity, quantum tunneling, and spin dynamics. But even they have limits. Beyond a certain point, thermal gradients vanish, and the very concept of heat flow breaks down. The machine reaches its own horizon. Then adiabatic demagnetization, a method born from the marriage of magnetism and entropy. Certain paramagnetic salts contain atoms with magnetic Momensteiny internal compasses. When exposed to a strong magnetic field at low temperatures, these moments align, reducing the system's entropy. Then, when the field is slowly removed in isolation, the atoms scramble to re-randomize, but with no external energy source. They must draw from their own thermal energy. The result: a plunge in temperature. Using this technique, physicists in the 1930s achieved temperatures below 0.001 Kelvin. By the 1950s, nuclear adiabatic demagnetization, applying the same principle to atomic nuclei, rather than electrons, reached 0.00002 Kelvin, just millionths of a degree above absolute zero. At such extremes, time distorts. Atomic vibrations stretch into perceptible oscillations. The distinction between particle and wave blurs. But humanity was not done. A new tool emerged, one that did not cool bulk matter, but individual atoms. Laser cooling. At first glance, it defies intuition. Lasers are associated with heat, with cutting, burning, igniting. Yet, in the hands of quantum physicists, they became instruments of profound cold. The principle hinges on momentum transfer. Photons carry energy and momentum. When an atom moving toward a laser beam absorbs a photon, it receives a tiny kick in the opposite direction, slowing it down. By surrounding atoms with lasers from all sides, what is known as optical molasses scientists can trap and decelerate them, reducing their kinetic energy dramatically. In 1978, researchers at Bell Labs demonstrated laser cooling of sodium atoms. By 1985, Stephen Shu, Claude Cohen-Tanuji, and William Phillips refined the technique, earning a Nobel Prize for their work. They achieved temperatures in them Kelvin range, a millionth of a degree above absolute zero. But even that was not enough. To go further, another step was needed: evaporative cooling. Just as blowing on hot soup removes the fastest moving molecules, leaving the rest cooler, physicists selectively eject the most energetic atoms from a trapped cloud. The remaining ensemble relaxes to a lower average temperature. Combined with magnetic traps and laser confinement, this method enabled the first creation of a Bose-Einstein condensate back in 1995. For decades, BECs existed only in theory. Predicted by Satyendra Nath Bose and Albert Einstein in 1924 to 1925, they described a state of matter in which bosonic atoms particles that can occupy the same quantum state collapse into a single macroscopic wave function when cooled sufficiently. At that point, millions of atoms behave as one coherent entity, like a single superatom visible under a microscope. When Eric Cornell, Carl Wieman, and Wolfgang Ketterall independently produced BECs using rubidium and sodium atoms at temperatures around 50 nanokelvin, the scientific world stood in awe. Here was matter transformed, not frozen, but unified. Quantum effects, normally confined to the scale of electrons and photons, now spanned hundreds of micrometers. Wave-particle duality became tangible. Interference patterns formed between separate condensates, proving they were not collections of particles, but singular quantum objects. This was not just cold, it was revelation, and yet the cost of each new milestone grew steeper. Every fraction of a degree closer to absolute zero demanded exponentially greater effort, more shielding, more vacuum, more precision. Cooling from 1 Kelvin to 0.1 K might take minutes. From 0.1 K to 0.01 K, hours. From there to microkelvin days. Reaching nanokelvin regimes requires weeks of gradual manipulation, constant monitoring, and flawless isolation from any external disturbancy and the faintest vibration from a footstep or passing truck. The deeper scientists ventured, the more nature resisted. It is as if the universe enforces attacks on cold, an entropy toll collected in time, energy, and complexity. The third law of thermodynamics is not merely mathematical, it is felt. Each attempt to extract the last traces of heat becomes harder, slower, more fragile. Systems resist equilibrium. Thermal contact vanishes. Instruments lose sensitivity. The signal fades into noise. And so, progress slows. Not due to lack of will, but because the universe itself tightens its grip. Yet, in the midst of this struggle, a startling realization emerged: nature has already gone colder than any laboratory on Earth. Not in the heart of a cryostat, not in a quantum trap, but in the vast, silent expanses between stars. Interstellar space, long thought to be cold, revealed itself to be far colder than anticipated. The Boomerang Nebula, a pre-planetary nebula 5,000 light-years away, holds the record for the coldest known natural place in the universe. Expanding gas from a dying red giant star has undergone adiabatic cooling on a cosmic scale, rushing outward so rapidly that it has chilled to just 0.97 Kelvin, colder than the 2.7 Kelvin glow of the cosmic microwave background. Here, without lasers or magnets, nature achieves what took humanity centuries to replicate. The nebula radiates faintly in submillimeter wavelengths, a ghostly whisper detected by the Atacama Large Millimeter Array, ALMI in Chile. Its bipolar lobes stretch across light years, a stellar breath frozen mid-exhalation. Even more profound are the conditions inside a dark molecular clouds, dense regions where stars are born. Shielded from starlight, their interiors hover near 10 Kelvin, but in rare pockets, radiative cooling and gravitational isolation allow temperatures to dip below 5 Kelvin. Within them, carbon monoxide and water ice form on dust grains, while hydrogen molecules rotate at glacial speeds, their spectra revealing the faint hum of near-zero motion. These are not just cold places. They are laboratories of quantum chemistry. At such temperatures, reactions that would be impossible on Earth occur with eerie efficiency. For instance, the formation of molecular hydrogen HN, the most abundant molecule in the universe, relies on dust grains acting as catalysts, allowing atoms to meet, bond, and release energy in environments too cold for classical collisions. Without these frigid nurseries, galaxies could not form stars. The cosmos would remain dark. And then there is the void. The great intergalactic deserts, where matter thins to less than 1 atom per cubic meter. Here, the dominant temperature is set not by local conditions, but by the fossil radiation of the Big Bang, the cosmic microwave background, CMB, which permeates all space at 2.725 Kelvin. This is the baseline temperature of the universe, a remnant heat stretched thin by 13.8 billion years of expansion. But even this is not the end. In shadowed craters near the moon's poles, permanently shielded from sunlight, NASA's Lunar Reconnaissance Orbiter measured temperatures as low as 30 Kelvin. Among the coldest places in the solar system, these pits may harbor ancient water ice, preserved since the early days of the solar nebula. And in the outer reaches, Pluto's surface dips to 33 Kelvin, where nitrogen and methane freeze into soft glaciers that flow like ice on Earth. New Horizons data revealed complex geology shaped by cryovolcanism. Eruptions not of lava, but of slushy volatiles driven by internal heat in a world where hot means barely above absolute zero. Yet, despite these natural extremes, no place in the observable universe reaches true cold. The CMB ensures that even the deepest voids are gently warmed. Cosmic rays trickle in. Starlight, though faint, persists. The universe refuses complete darkness. Which is why, paradoxically, the coldest places in existence are not in space, but in orbit. On board the International Space Station, floating in microgravity 400 kilometers above Earth, resides the Cold Atom Labs, CALE, a compact, suitcase-sized facility developed by NASA's Jet Propulsion Laboratory. Since 2018, it has been producing Bose-Einstein condensates in conditions impossible on the ground. Why space? Because gravity interferes. On Earth, even the most delicate traps must hold atoms against their weight. Magnetic and optical fields require immense strength just to prevent collapse. But in freefall, atoms float freely. Traps can be weaker, evaporation more efficient, observation times longer. In sail, rubidium and potassium atoms are laser-cooled, magnetically trapped, and evaporatively cooled to temperatures below 100 picokelvin, that is, 0.1 Kelvin. At this scale, atomic motion slows to centimeters per second. Quantum wave functions expand to millimeters in size, visible to detectors. Coherence lasts for seconds, even tens of seconds, allowing unprecedented study of quantum phenomena. One experiment observed quantum interference between separate condensates, confirming their wave, like nature over macroscopic distances. Another probed quantum bubbles, exotic states where atoms arrange into hollow shells governed by quantum pressure. Others test the equivalence principle, searching for deviations from general relativity at microscopic scales. CAL is not just a lab, it is a portal. A window into a domain where time stretches, where matter flows like liquid light, where the rules of classical intuition dissolve. And yet even here, absolute zero remains unreachable. Each success underscores the impossibility. The colder the system, the more isolated it must be. From light, from magnetic fields, from vibration, from measurement itself. Because observation introduces energy, detection disturbs, the act of knowing warms. There is a deep irony in this quest. The more we learn about cold, the more we realize how much heat contaminates knowledge. Perhaps that is the essence of the mystery. The machines built to chase the impossible do not fail. They succeed by revealing that the goal was never to arrive. It was to understand the journey. Every dilution refrigerator, every laser array, every orbital experiment adds another layer to the story, that cold is not a destination, but a process, a negotiation between order and chaos, between control and uncertainty. And in that negotiation, something unexpected emerges, not just new states of matter, but new questions. Can information survive at near zero temperatures? Could quantum memories store data indefinitely in BECs? Is there a connection between ultra-cold physics and the early universe, where quantum fields underwent phase transitions similar to those in condensates? Could artificial systems mimic the conditions of cosmic inflation, testing theories of quantum gravity in tabletop experiments? These are no longer speculative dreams. They are active lines of research. At institutions like MIT, NEST, and the Max Planck Institute, teams use ultra-cold atoms to simulate black hole event horizons, creating analogs of Hawking radiation in flowing quantum fluids. Others model neutron star crusts using degenerate fermionic gases, probing the equation of state of matter under extreme density. Cold, once a mere absence, has become a tool, a canvas, a laboratory for the laws of everything. And still, the wall stands, absolute zero, unattainable, forbidden, silent. But in its shadow, science thrives. For in striving to touch the unattainable, humanity does not conquer nature, it listens. And in the faint tremor of an atom slowed to near nothingness, in the coherence of a million particles becoming one, in the quiet hum of a machine pushing against the edge of possibility, there is a kind of reverence, not for cold, but for the universe that makes it both necessary and impossible. A universe that allows us to get close, but never close enough. And perhaps in that distance lies its greatest truth. There is a cold so deep it does not freeze matter but unravels time. A cold not of winter, nor of shadow, but of absence. Not the absence of light, nor of life, but of motion itself. It lingers at the edge of every measurement, just beyond the reach of instruments, whispering from the equations like a forgotten law. It is absolute zero, 0 Kelvin, the theoretical end of temperature, where atomic motion ceases, entropy halts, and change dissolves into stillness. And yet, the universe refuses to obey. For all the precision of human engineering, for all the silence of interstellar voids, absolute zero remains untouched. Not merely unachieved, unachievable, a mathematical horizon, always receding, never crossed. The closer science gets, the more nature resists not with force, but with principle. This is not failure, it is revelation, a growing understanding that cold is not simply a condition to be mastered, but a boundary inscribed into the cosmos itself, limit not of machines, but of existence. The story begins with a glow, faint, omnipresent, whispering from the first moments of time. In 1965, Arno Penzias and Robert Wilson, tuning a radio telescope in Holmdel, New Jersey, detected a persistent hiss-a-low hum that refused to vanish. No matter where they pointed their antenna, it came from everywhere and nowhere, uniform, unchanging. After months of troubleshooting, cleaning pigeon droppings, recalibrating circuits, eliminating interference, they realized this was not noise, it was signal, the afterglow of creation, the cosmic microwave background, CMB relic radiation from the Big Bang, permeates the entire observable universe at a temperature of precisely 2.725 Kelvin. This is the baseline chill of space, the ambient temperature of the void, not because space is cold in the way we understand, but because expansion has stretched primordial light into microwaves, cooling it over 13.8 billion years, from thousands of degrees to just above absolute zero. This number 2.7 K is not arbitrary. It is the thermal memory of the infant universe, a fossil heat bath, slowly fading, defining the lowest natural temperature most regions can ever reach. Any object adrift in deep space, shielded from stars, will eventually equilibrate to this temperature. It is the floor, or so it seemed. But nature, in its quiet rebellion, has gone colder far beyond the solar system. In the constellation Centaurus lies a ghostly hourglass of gas known as the Boomerang Nebula, dying star casting off its outer layers in a supersonic wind. Here, something extraordinary happens. As the gas expands at nearly 160 kilometers per second, it undergoes Soderbeck cooling. The rapid outward rush converts thermal energy into kinetic energy, siphoning heat from the system faster than radiation can refill it. The result? A region of space chilled to 0.97 Kelvin colder than the CMB itself. It is a paradox written in ice. How can any place in the universe be colder than the cosmic background? Because the CMB is not a heater. It is a reservoir. And if a system cools faster than that reservoir can warm it by expanding, radiating, or isolating, then, for a time, it slips below the universal floor. The Boomerang Nebula is not absorbing microwaves. It is radiating its own energy into the dark, like a cup of coffee left in a freezer. It loses heat faster than the environment returns it. But unlike the coffee, there is no door to close. The nebula is open to the cosmos and, yet, for now, it remains colder. This makes it the coldest known natural place in the universe. But even here, atoms move. Photons trickle in. The faint pressure of starlight, the occasional cosmic ray, the inexorable pull of gravity, all conspire to warm it ever so slowly. Perfect cold does not exist in nature, only nearness. And yet, humanity in its laboratories has gone far colder, not by expansion, not by isolation, but by design. In sealed vacuum chambers on Earth, physicists have achieved temperatures measured in a nanokelvin's billionths of a degree above absolute zero. In 2018, the Cold Atom Lab aboard the International Space Station recorded clouds of rubidium atoms at 100 picokelvin, or 0.00000001 K. At such extremes, time dilates. Atomic vibrations stretch into seconds. Quantum wave functions swell to visible sizes, overlapping like ripples on a frozen pond. These are not natural conditions. They are acts of defiance, engineered stillness, and yet still not zero. No matter how refined the apparatus, no matter how perfect the isolation, the final fraction of a degree remains out of reach. Cooling becomes not harder, but infinitely harder. Each step demands exponentially more effort, more shielding, more control, more time. This is not a technological limitation. It is a law. The third law of thermodynamics states clearly, absolute zero cannot be reached in a finite number of steps. It is an asymptotic, endless approach, like dividing a distance in half, then half again, forever approaching a point you never touch. Scientists do not speak of reaching zero anymore. They speak of approaching it, of dancing at its edge, and in that dance, they confront a deeper truth. The universe resists completion. To achieve absolute zero would require the total cessation of motion, no vibration, no rotation, no quantum fluctuation, a state of perfect order, perfect stillness, perfect entropy, minimum. But such a state violates quantum mechanics. Werner Heisenberg's uncertainty principle forbids it. If a particle were truly at rest, its position and momentum would both be known with infinite precision and impossibility. Therefore, even in the deepest cold, particles retain zero-point energy, a residual hum mandated by wave-particle duality. Electrons continue to orbit, atoms vibrate, fields fluctuate, even the vacuum is not empty. Quantum field theory reveals that space is filled with virtual particles, fleeting fluctuations of energy that blink in and out of existence. Borrowing from the uncertainty principle, these are not mere abstractions. They produce measurable effects. The Casimir force, the Lamb shift, spontaneous emission, all powered by the restless energy of nothingness. Thus, absolute zero is not just unreachable, it is incoherent, a contradiction in terms, a mathematical ideal with no physical counterpart, and so the escalation becomes clear. While nature can create pockets colder than the average universe, like the Boomerang Nebula, nature nor humanity can breach the final threshold. The coldest places in existence are not defined by how low they go, but by how close they come to a limit they can never cross. This is the great paradox of cold. We live in a universe where space can be colder than the universe. Where laboratories on Earth achieve temperatures billion times lower than the ambient glow of the cosmos, yet still fall infinitely short of zero. It is not irony, it is symmetry, a balance between possibility and prohibition. Consider the implications. If absolute zero were attainable, what would happen? Atoms would stop, electrons would collapse, quantum coherence would vanish. Time, in a sense, would lose meaning, because change requires energy difference, and at zero, no gradient exists. No work could be done, no signal sent, no thought formed. It would be the end of physics, and perhaps the end of being. Some cosmologists speculate that in the far, far future, trillions upon trillions of years from now, after black holes evaporate via Hawking radiation and protons, the COVID universe may approach a state called heat death, maximum entropy, uniform temperature, no free energy, a dark, dilute sea of photons and leptons, cooled to near zero. But even then, models suggest the temperature will not reach zero. Residual vacuum, energy possibly tied to dark energy, may prevent it. The cosmological constant implies a minimum energy density in space. True equilibrium may never occur. Absolute zero, then, is not just physically impossible. It may be eternally forbidden. A singularity of stillness that the cosmos avoids by design, and yet scientists continue to chase it, not to break the law, but to understand it. Each new record picokelvin milestone is not a step toward victory, but a deeper inquiry into the nature of reality. The machines built to cool atoms are not just refrigerators. They are microscopes, time machines, simulators of the early universe. At nano-Kelvin temperatures, Bose-Einstein condensates form quantum states where millions of atoms merge into a single wave function. These are not just curiosities. They are analogs of the Higgs field, of superconductivity, of neutron star matter. They allow physicists to simulate phase transitions that occurred fractions of a second after the Big Bang. Others use ultra-cold fermions to model high-temperature superconductors, seeking materials that could revolutionize energy transmission. Still others probe the quantum vacuum, testing whether virtual particles can be manipulated or even harnessed. But the most profound experiments ask philosophical questions. Can time emerge from stillness? Is information preserved at near zero temperatures? Could a quantum computer operating near absolute zero simulate a universe? These are not fantasies, they are active investigations, and in them, the impossibility of absolute zero takes on new meaning. It is not a wall, it is a mirror reflecting back the structure of physical law. In 1900, Max Planck introduced the idea that energy is quantized, not continuous, but discrete. This small assumption birthed quantum mechanics. One consequence: cooling is not smooth. Energy is removed in packets. As temperature drops, the gaps between energy levels grow larger than the remaining thermal energy. There comes a point when no further quanta can be extracted. The system is trapped in its ground state not because it has reached zero, but because it cannot shed the last vestige of energy without violating quantum rules. Einstein later showed that even at absolute zero, systems retain zero-point motion. In his 1913 paper on specific heats, he demonstrated that quantum oscillators never fully freeze. The implication was radical. Motion is inherent to existence. Cold, then, is not the opposite of heat. It is a different expression of energy, a regime where quantum order dominates, where coherence replaces chaos, where the universe speaks in waves instead of particles. And in this light, the inability to reach zero becomes not a failure, but a feature. Without residual motion, there would be no quantum fluctuations, no vacuum energy, no possibility of structure, no galaxies, no life. Perfect stillness is sterile. The universe thrives on imbalance, on difference, on the very gradients that drive change, which is why, in the end, the quest for absolute zero is not about cold at all. It is about boundaries, about the edges of what is possible. When scientists describe the third law, they do not lament their inability to reach zero. They marvel at the consistency of nature, that across scales from subatomic particles to interstellar clouds, the same principles hold, that entropy behaves predictably, that quantum mechanics enforces its rules without exception. This is not resistance, it is reliability. A universe that limits itself is a universe that can be understood. And so, the machines continue to run. Dilution refrigerators hum in underground labs. Laser, ARRA, wise pulse in vacuum chambers. Satellites orbit, carrying Bose-Einstein condensates through silent arcs around Earth. Each experiment is an act of reverence, not for cold, but for the laws that make it both desirable and unattainable. In the faint tremor of an atom slowed to a crawl, in the coherence of a million particles moving as one, in the silence between measurements, there is a kind of awe, not for mastery, but for mystery, because in striving to touch the unattainable, science does not conquer nature, it listens, and what it hears is not silence, but a hum, low, persistent, sound of a universe that will never stop moving, even at its coldest, even at its quietest, even when it tries. In the deepest silence between stars, where light dwindles to a whisper and motion slows to a crawl, there exists a phantom threshold of cold, so absolute it has never been touched. Not by nature, not by machine, not even in the vast, empty reaches of intergalactic space. This is 0 Kelvin, absolute zero. A temperature so low that all classical motion should cease, every atom frozen into perfect stillness. And yet, across the universe, this state remains unreachable, like a horizon always receding before us. Not because we lack the tools, but because something deeper resists its arrival. The laws of physics themselves seem to forbid it. The third law of thermodynamics stands as both sentinel and riddle at this frontier. Formally articulated by Walther Nernst over a century ago, it declares that as a system approaches absolute zero, its entropyth measure of disorder, of hidden chaos within matter approaches a constant minimum, but crucially, it can never reach zero. Not asymptotically, not with infinite patience. The law does not merely describe difficulty. It implies impossibility. It is not an engineering limitation. It is a principle woven into the fabric of reality. To achieve 0 Kelvin would require removing every trace of thermal energy, every quiver of atomic agitation. Yet no matter how far we cool, no matter how precisely we isolate, some residual tremor persists. A ghost in the machine, a vibration beneath the silence. And now, quantum mechanics steps forward, not to solve the mystery, but to deepen it. For long before the third law was formalized, the seeds of resistance were already planted in the strange soil of the subatomic world. In 1927, Werner Heisenberg unveiled his uncertainty principle, a fundamental limit on how precisely we can know certain pairs of physical properties, position and momentum, energy and time. At first glance, it seems abstract, mathematical, but its consequences are tangible, chilling. When applied to temperature, it means that particles cannot ever come to complete rest. If they did, we would know both their position and momentum with perfect precision, an outright violation of quantum law. So instead, even at the edge of cold, atoms shiver with what physicists call zero-point motion, not from heat, not from external influence, but from existence itself. This is not mere theory. It has been measured, observed in superfluid helium, cooled to within billionths of a degree above absolute zero. The liquid still flows without viscosity, climbing walls and dripping through sealed containers, not due to thermal energy, but because of quantum tunneling and zero-point fluctuations. In trapped ion experiments, lasers cool single atoms to temperatures colder than deep space, yet their electrons continue to jitter, their nuclei vibrate with irreducible energy. Even in the vacuum of space, devoid of matter, the electromagnetic field hums with residual activity. Virtual particles blink in and out of existence, borrowing energy from the void for fleeting instants allowed by the uncertainty principle. These are not anomalies. They are signatures of a universe that refuses stillness. Consider, then, the implications. Absolute zero is not simply a very cold temperature. It is a state of total cessation, a world without movement, without change, without time. But if quantum mechanics insists that particles must retain motion even at the lowest conceivable energies, then reaching 0 Kelvin would require suspending the rules that define matter. It would be like asking a river to exist without flow, or light to travel without waves. The universe, it seems, does not permit such contradictions. Some have speculated, could we cheat? Could advanced civilizations, far beyond our own, devise methods to circumvent this limit? Perhaps by manipulating space-time itself, or isolating systems in ways we cannot yet conceive. There are thought experiments, some bordering on science fiction, that explore these possibilities. One imagines a perfectly reflective cavity, shielded from all external radiation, containing a single atom suspended in darkness. With each passing moment, it emits a photon, losing energy, cooling further. Given infinite time, might it approach absolute zero? But even here, the vacuum intervenes. Quantum fluctuations generate black body radiation at every temperature, however low. The cosmic microwave background, a faint afterglow of the Big Bang at 2.7 Kelvin, permeates all space. Shielding a system from it completely is impossible. Any container, no matter how perfect, will eventually exchange photons with the vacuum, introducing infinitesimal but inexorable heat. Even in the coldest known natural environment, the Boomerang Nebula, where gas expands at supersonic speeds, cooling to just 1 degree above absolute zero, atoms still move. Their rotational states remain excited. Spectral lines reveal not stillness, but a slow, dignified dance. Nanokelvin temperatures billionths of a Kelvin. At these extremes, quantum effects dominate. Atoms lose their individual identities, merging into a single coherent wave known as a Bose-Einstein condensate. Here, matter behaves less like particles and more like a shimmering fog of probability. And yet, this is the paradox. Even in this most ordered, coldest state humans have ever created, zero-point energy remains. The condensate does not vanish into stillness. It pulses with quantum life. What, then, does it mean that absolute zero cannot be reached? Is it merely a technical barrier, or does it point to something more profound? Some physicists suggest that the unattainability of 0 Kelvin is not just a thermodynamic rule, but a reflection of time's arrow. Entropy increases, disorder spreads, but at absolute zero, entropy would be minimized, possibly halted. Time, which emerges from change, might lose its meaning. No motion, no decay, no signal propagation. In such a state, causality itself could unravel. Events would not follow one another. The future would not differ from the past. It would be a timeless void, an end, not only to temperature, but to sequence, to narrative, to becoming. There is a haunting symmetry here. At the highest energies, the first moments of the Big Bang time also breaks down. Our equations fail. General relativity clashes with quantum mechanics. Singularities form, and at the opposite extreme, near absolute zero, the same collapse occurs. Both extremes defy description. Both represent boundaries beyond which our understanding falters. Perhaps 0 Kelvin is not a destination, but a horizontal limit beyond which physics as we know it dissolves. Like the event horizon of a black hole, it marks a boundary of knowledge, not just of temperature. And if that is true, then the prohibition against reaching absolute zero may be more than a physical constraint. It may be a safeguard, a cosmic rule, preserving the conditions necessary for reality to unfold. Without motion, there is no chemistry. Without fluctuation, no structure formation. Without uncertainty, no possibility. The universe thrives on imperfection, on instability, on the restless hum of quantum fields. Remove that, and you remove the potential for stars, for planets, for life. Absolute zero is not just cold, it is sterile, inert, dead. Laboratories around the world push closer, not to break the law, but to test its edges. In 2017, researchers at MIT cooled a sample of sodium-potassium molecules to 500 nanokelvin, observing exotic quantum behavior. In 2021, NASA's Cold Atom Lab aboard the International Space Station achieved temperatures below 100 picokelvin trillionths of a degree above zero, leveraging microgravity to extend observation times. Each step reveals new phenomena, quantum phase transitions, novel forms of superconductivity, hints of dark energy analogs in lab-created vacuums. We do not seek absolute zero to conquer it. but to understand why it eludes us, to listen to the whispers of the vacuum, to feel the pulse of zero-point energy, and ask, what kind of universe insists on motion? Could alien civilizations have found a way? Might beings who mastered space-time manipulation, who harnessed negative energy or engineered false vacuums, bypass this limit? Science fiction offers visions of cryo-arrested minds, of civilizations sleeping in eternal ice, but real physics suggests otherwise. The Heisenberg uncertainty principle is not a human invention. It is embedded in the commutation relations of quantum operators' mathematical truths that appear universal. Unless the laws of physics vary across the cosmos, a possibility not ruled out by current data. Though unsupported, any intelligent observer, anywhere, would encounter the same barrier. Absolute zero is not a technological challenge. It is a law of being. Some theorists go further. They propose that the unattainability of 0 Kelvin is linked to deeper cosmic mysteries, such as vacuum decay. According to quantum field theory, our universe may reside in a false vacuum metastable state that could, under certain conditions, collapse into a lower energy-true vacuum. Such a transition would propagate at the speed of light, rewriting the laws of physics in its wake. While speculative, this idea arises from real calculations in the Standard Model. And curiously, the stability of the vacuum is tied to temperature. At absolute zero, if it could exist, the vacuum might become unstable, triggering decay. Thus, the impossibility of reaching 0 Kelvin could act as a cosmic failsafe, preventing a catastrophic phase transition. Reality, in other words, may be protected by its own inability to freeze. Others draw connections to black holes. At their singularities, density becomes infinite. Space-time curvature diverges in temperature, according to Hawking radiation theory, approaches absolute zero only in the infinite future. A black hole cools as it evaporates, but never quite reaches zero. Its final moments remain hidden behind quantum uncertainty. Once again, the limit appears. Not just in labs, not just in equations, but in the fate of dying stars. The universe seems to enforce a universal rule. Nothing real can stop moving. Not entirely. Not forever. Then there is the philosophical weight of it all. Why should the universe abhor perfect stillness? Is it possible that motion is more fundamental than matter? That time is not a dimension, but a consequence of fluctuation? Some interpretations of quantum gravity suggest that space-time itself emerges from entangled quantum states, networks of relationships that require interaction, exchange, change. No change, no space-time, no zero-point energy, no universe. In this view, the refusal of absolute zero is not a limitation, but a necessity. The cosmos is built on vibration, on rhythm, on the eternal hum of existence. And so, the quest continues not to reach zero, but to understand why we cannot. Each experiment, each refinement, peels back another layer of the mystery. We cool atoms not to freeze them, but to watch them behave in ways that defy intuition. We trap ions not to silence them, but to hear the music of their quantum vibrations. In the laboratory, in the quiet hum of cryogenic chambers, scientists are not just testing thermodynamics. They are probing the edge of reality. Perhaps, then, absolute zero is not a place, but a mirror. It reflects back our deepest assumptions about order, about time, about what it means for something top. We imagine it as perfection, a flawless crystal of stillness. But nature suggests otherwise. Perfection in this universe is not stillness. It is motion. It is flux. It is the delicate balance between chaos and coherence, maintained by the faintest tremors of quantum energy. And so, the universe breathes, even in the coldest dark between galaxies, where photons stretch thin and stars fade. The vacuum thrums with potential. Particles flicker. Fields oscillate. The zero-point energy lingers unseen, untouchable but undeniable. It is the last heartbeat of a cosmos that refuses to die, that refuses, even in principle, to stop. To reach absolute zero would be to extinguish that pulse, to halt the dance of existence. But the universe, it seems, will not allow it. Not now, not ever. The third law is not merely a scientific statement. It is a testament, a declaration written in the language of entropy and uncertainty. Motion is eternal, and in that truth there is wonder, not in the conquest of cold, but in the realization that even at the edge of nothing, something persists, a whisper, spark, a universe still alive. In the silent heart of laboratories scattered across Earth, and one floating above its scientists wage a quiet war against heat, not with fire or force, but with light, magnetism, and the subtle choreography of atoms cooled to within a breath of stillness. These are not experiments in temperature alone. They are voyages into the deep structure of reality, where the rules of the everyday dissolve and quantum strangeness takes hold. The goal is no longer merely to reach absolute zero, a prize physics itself forbids, but to walk as close to its edge as possible, to peer over into the abyss of near motionless matter and ask what remains when almost everything stops. This pursuit has birthed technologies so precise, so delicate, they resemble art. At their core lies a simple truth. To cool is to remove motion. Every degree lowered strips away kinetic energy, slows atomic dance, quiets the chaos of vibration. But as temperatures plunge into the nanokelvin range, billionths of a degree above zero, classical methods fail. Refrigerators, powered by compressing gases, cannot go this far. Instead, scientists turn to the quantum toolkit: laser cooling, magnetic traps, evaporative techniques, and the counterintuitive power of measurement itself. Laser cooling stands as one of the most elegant paradoxes in modern physics. Light, often associated with warmth and energy, becomes the agent of cold. When tuned precisely to specific atomic transitions, laser beams can act like an invisible molasses, slowing atoms as they move toward the photons. Each collision transfers momentum, nudging the atom backward like running into a steady rain. By surrounding a cloud of atoms with 6 laser beams, 2 along each spatial axis, researchers create what is known as optical molasses. In this glowing cage, atoms that were once moving at hundreds of meters per second slow to mere centimeters per second. Their temperature drops from room temperature to just a few hundred microkelvin colder than interstellar space. But even this is not enough. To descend further, scientists employ Doppler cooling, exploiting the relativistic shift in light frequency caused by motion. Atoms moving toward a laser perceive its light slightly. Those moving away see it redshifted. By tuning the laser just below the resonant frequency of the atom, only those approaching will absorb photons, slowing them down. It is a feedback loop of deceleration, a self-correcting trap where faster atoms are targeted while slower ones pass through untouched. The result is a gradual thermal collapse, dimming of atomic motion until the gas hovers barely above absolute zero. Yet, laser cooling alone hits a limit where the very photons used to cool begin to impart random kicks, reheating the system. To break through, physicists deploy a second stage, evaporative cooling. Imagine a cup of coffee steaming in the air. The hottest molecules escape first, carrying energy with them. The remaining liquid grows cooler. In ultra-cold labs, the same principle applies, but with exquisite control. Trapped atoms are held in magnetic or optical fields, and the most energetic ones are selectively removed, allowing the rest to rethermalize at lower and lower temperatures. Like letting the fastest runners leave a race, the average speed of the pack decreases. Through this method, clouds of rubidium or sodium atoms have been cooled into the nanokelvin regime, so cold that quantum effects dominate entirely. At these temperatures, something extraordinary occurs. The atoms lose their individuality. Their de Broglie wavelengths, quantum measures of their wave-like nature, until they overlap. Suddenly, millions of particles merge into a single macroscopic quantum state, a Bose-Einstein condensate. Beck first predicted in 1924 and realized experimentally in 1995. BSEs behave not as discrete particles, but as a coherent waiver superatom, visible under microscopes, shimmering like liquid light. In this state, quantum mechanics is no longer hidden beneath statistics. It is on display. Atoms tunnel through barriers, interfere like ripples on a pond, and exhibit superfluidity, flowing without friction, climbing walls, defying gravity. These condensates are not just curiosities. They are probes. Laboratories use them to test the foundations of quantum theory, searching for deviations that might hint at new physics. Some experiments investigate whether gravity behaves differently at microscopic scales. Could it be quantized? Others look for evidence of wave function collapse, testing theories like continuous spontaneous localization, CSL, which propose that quantum superpositions naturally decay over time. If such models are correct, BECs should show tiny anomalies in their coherence. None have been found yet, but the search continues, inching closer to energies where quantum gravity might whisper. Another frontier lies in sympathetic cooling, a technique borrowed from thermodynamics but refined to atomic precision. Here, two species of atoms or ions are trapped together. One is laser-cooled directly. The other, which may not interact well with light, cools indirectly through collisions with its partner. It is thermal empathy at the quantum level. Energy flows from the warm to the cold, not by design, but by necessity. This method has enabled the cooling of molecular ions, complex systems that resist traditional approaches. And because molecules possess rich internal structures, rotational and vibrational states, they offer new avenues for studying quantum chemistry, precision spectroscopy, and even the variation of fundamental constants over time. But Earth's gravity imposes limits. Even in the best vacuum chambers, atoms fall. Observation times are short milliseconds, sometimes less. To extend them, scientists needed to escape the pull of the planet. So, in 2018, NASA launched the Cold Atom Lab (CAL) to the International Space Station, a compact refrigerator-sized facility designed to produce ultra-cold quantum gases in microgravity. Without gravity, atoms float. Traps can be weaker. Evaporation more efficient. Observation windows stretch from milliseconds to seconds. For the first time, researchers could watch quantum phenomena unfold in slow motion. CAL has already achieved temperatures below 100 picokelvin, 1/10 of a billionth of a Kelvin month, the coldest ever recorded. In this environment, atoms drift lazily, their wave functions expanding to millimeter scales. Quantum vortices form in matter wave interferometers achieve unprecedented sensitivity. And because CAL is remotely operated, multiple research teams can conduct experiments in orbit, testing everything from dark energy analogs to the equivalence principle in quantum regimes. The implications ripple outward. Ultra-cold atoms are not just tools for pure science, they are shaping the future of technology. Atomic clocks based on laser-cooled strontium and ytterbium now lose less than 1 second. Every 15 billion years more precise than the age of the universe. These clocks test general relativity, detecting time dilation over height differences of just 1 millimeter. They may one day detect gravitational waves from the early cosmos or reveal dark matter interactions through tiny frequency shifts. Meanwhile, magnetic refrigeration offers a terrestrial path toward extreme cold without the need for hazardous cryogens. Based on the magnetic Lorenz effect, it uses magnetic fields to align atomic spins, reducing entropy. When the field is removed, the material absorbs heat from its surroundings, cooling them, though not yet capable of reaching nanokelvin temperatures. This technology is being explored for next-generation cooling systems in space missions and quantum computers, where stability and efficiency are paramount. And then there are particle accelerators machines that seem to belong to the world of high energy, not low temperature. Yet here too, cold plays a crucial role. Superconducting magnets, essential for guiding and focusing particle beams in colliders, like the Large Hadron Collider, LHC, must operate near absolute zero. At 1.9 Kelvin colder than outer space, niobium titanium coils enter a superconducting state, conducting electricity without resistance. This allows immense magnetic fields to be sustained with minimal energy loss. The entire 27-kilometer ring of the LHC is bathed in liquid helium, a cryogenic circulatory system maintaining a temperature just above the unreachable zero. Without this cold, the LHC could not function. Without superconductivity, the energies needed to probe the Higgs boson, search for supersymmetry, or explore quark-gluon plasma would be unattainable. Thus, the quest for the hottest moments of the Big Bang is inextricably tied to the mastery of the coldest conditions in the present universe. Fire demands ice. Creation requires stillness. But beyond engineering, these extremes serve a deeper purpose. They are stress tests for physics itself. As systems approach absolute zero, long-buried assumptions surface. Does time dilate differently for ultra-cold atom? Do quantum fluctuations couple to gravity in unexpected ways? Could the vacuum energy shift at near-zero temperatures, revealing connections between quantum field theory and cosmology? One tantalizing possibility involves vacuum birefringence, a prediction of quantum electrodynamics (QED) that suggests empty space becomes polarized in strong magnetic fields, acting like a crystal for light. Experiments using ultra-cold plasmas and high-field magnets aim to detect this effect, potentially confirming nonlinear properties of the quantum vacuum. If observed, it would mean that even empty space has structure, one that might be influenced by temperature. However, indirectly, other experiments search for fifth forces, hypothetical interactions beyond gravity and electromagnetism that might emerge at low energies. Some theories suggest that dark energy, responsible for the accelerating expansion of the universe, could manifest as a weak, long-range force detectable only in meticulously shielded, ultra-cold environments. By suspending nanoparticles in optical traps and cooling them to their quantum ground state, researchers hope to sense accelerations smaller than 1020 meter per second squared, sensitive enough to catch the whisper of new physics. There is also growing interest in simulation using ultra-cold atoms in optical lattice patterns of light formed by interfering lasers to mimic the behavior of electrons in exotic materials. These artificial crystals allow scientists to model high-temperature superconductivity, topological insulators, and even black hole analogs. In some setups, sound waves in BCS behave like particles near an event horizon, emitting Hawking radiation in the lab. While not identical to astrophysical black holes, these analogs provide testbeds for ideas otherwise inaccessible. All of this, the lasers, the traps, the orbital labs, the superconducting rings, points not toward the conquest of cold, but toward understanding. The third law of thermodynamics ensures that absolute zero will never be reached. But in the approach, in the slow descent through microkelvin, nanokelvin, picokelvin, new layers of reality peel back. Each decimal place reveals another facet of the quantum vacuum, another clue about the nature of time, entropy, and existence. And perhaps, in this pursuit, there is a deeper revelation that the universe does not value perfection. It values process. It thrives not on stillness, but on the tension between order and chaos, between energy and its absence. The tools we build, laser-cooled atoms, orbiting condensates, superconducting magnets, are not just instruments of measurement. They are acts of reverence, a way of listening to the faint hum of zero-point energy, of feeling the pulse of a cosmos that refuses to freeze. For in the end, the unattainability of absolute zero is not a failure, it is a signature, a mark left by the laws of nature, telling us that motion is fundamental, that uncertainty is woven into being, that even in the deepest cold, something stirs. And as long as that tremor persists, measured in billionths of a degree, sensed in the flicker of a trapped ion, the mystery endures. Not of how to stop the universe, but of why it never does. There is a silence the universe refuses to allow, not the quiet between words, nor the hush of snowfall at midnight, nor even the vast, echoing stillness between galaxies where light takes billions of years to cross empty space. No, this silence is deeper. It is the absence of motion, the end of vibration, the final pause in a cosmos built on rhythm. It is the sound of absolute zero, not cold as we feel it, but cold as a concept and idea, so pure, so absolute, that reaching it would unravel the very conditions that make reality possible. And yet, for all our machines, all our lasers and magnetic traps, all our orbital laboratories floating above the atmosphere like frozen lanterns, we cannot touch it. We can approach, draw near with exquisite precision, cool atoms until they drift like ghosts through optical lattice, slow time in atomic clocks until a second stretches across epochs, but we cannot cross. The third law stands immutable. Absolute zero remains beyond reach, not because of engineering limits, but because nature itself resists. It is forbidden, not by decree, but by design. In this impossibility, there is meaning. For centuries, humanity has chased perfection. We have sought flawless symmetry, eternal stillness, a state of being untouched by decay. We imagined gods who do not age, heavens without change, realms beyond entropy. But the universe tells a different story, one written in the jitter of electrons, the flicker of virtual particles, the irreducible hum of the quantum vacuum. Perfection, it seems, is not stillness, it is motion. Not order imposed from outside, but dynamic balance sustained from within. Life does not emerge from equilibrium mid a rhesus despite. It fueled by the very imperfections that drive stars to burn, rivers to flow, and minds to wonder. Absolute zero, then, is more than a temperature. It is a boundary, a threshold, not just of physics, but of existence. To reach it would be to halt time, for time requires change. Without transition, without cause and effect, without the arrow of increasing entropy, there is no before or after. There is only a... And if the Heisenberg uncertainty principle holds and every experiment confirms that it does, then, even at the edge of cold, particles retain energy. They vibrate, they fluctuate, they refuse to be pinned down. This is not a flaw. It is the foundation. The universe does not merely tolerate uncertainty, depends on it. Without it, matter would collapse into predictability, and predictability into stasis. And stasis is indistinguishable from non-existence. Consider the implications. The same law that prevents us from knowing both position and momentum also ensures that atoms never sleep. The same principle that shrouds the subatomic world in probability also keeps the cosmos alive. In this light, the unattainability of absolute zero becomes not a limitation, but a safeguard, a cosmic immune response against total stillness. The universe protects its own continuity by forbidding finality. This truth echoes through history. Einstein, who reshaped space and time, spent his final years searching for a unified theory, only to confront ever-deepening mysteries. He once said, "The most beautiful thing we can experience is the mysterious." He did not say solving the mystery. He said experiencing it. There was humility in that recognition that some boundaries are not meant to be crossed, but contemplated. Heisenberg, too, understood. His uncertainty principle was not a confession of ignorance, but a revelation of structure. The limits of measurement were not failures of science. They were signatures of reality. And so, the unreachable cold becomes a mirror. It reflects not our inadequacy, but our place within a universe that thrives on becoming. We are not meant to freeze time. We are meant to live within it, to witness its passage, to feel its pull, to leave ripples in its stream. The fact that we can cool atoms 2/trillionths of a Kelvin, nearly stop them, astonishing. That we cannot stop them completely is profound entropy. Often misunderstood as mere disorder, is better seen as the engine of transformation. It is why stars ignite, why oceans mix, why memory forms in the brain. Without entropy, nothing happens. Absolute zero would be the ultimate victory of entropy's opposite, not order, but stagnation. A universe without heat death would instead suffer motion death, a fate even more absolute. For in heat death, there is still fluctuation, however faint. In motion death, there is nothing. Yet even in the coldest voids, far from galactic centers, where the cosmic microwave background casts its feeble glow at 2.7 Kelvin, atoms still move. Molecules rotate. Electrons orbit. The vacuum seethes with quantum activity. Virtual particle pairs blink in and out of existence, borrowing energy from the void, repaying it in fleeting instants allowed by uncertainty. These are not exceptions. They are the rule. The universe does not permit emptiness. Even empty space teems with potential. The ground state is not silent, it sings in frequencies too low to hear. And perhaps that is the deepest lesson. Existence is not defined by what is achieved, but by what persists. Not by arrival, but by journey. Humanity may never stand at 0 Kelvin, but in striving toward it, we have discovered Bose-Einstein condensates, tested quantum gravity models, built clocks so precise they measure the curvature of space-time over a tabletop. We have learned that cooling is not destruction, but revelation. That by removing heat, we uncover layers of reality hidden beneath thermal noise. In this, there is poetry. The universe, in its vast indifference, has built-in resistance to finality. It does not allow complete rest. It does not permit perfect knowledge. It does not yield to total control. And in that refusal, there is grace. For if everything could stop, if time could freeze, if motion could cease, then life, consciousness, curiosity, love all would be impossible. They require flux. They feed on imbalance. They arise from the very imperfections that keep the quantum fields trembling at absolute zero's edge. Even black holes, those monuments to gravitational collapse, do not achieve true stillness. Hawking radiation whispers from their horizons, a quantum sigh emitted over eons. They evaporate, slowly, reluctantly, refusing to vanish without trace. Even in annihilation, there is emission. Even in darkness, there is light. So too with us. Our lives are brief, entropic, destined to fade. But in that brevity, we reach, we build, we question. We cool atoms to the edge of stillness, not to end motion, but to understand it. We gaze into the abyss of cold and see not emptiness, but structure, not silence, but signal. The fact that we cannot reach 0 Kelvin does not diminish the quest, sanctifies it. For the most meaningful journeys are not those that end at a destination, but those that reveal the nature of the path. Einstein and Heisenberg knew this. So did Nernst, who formalized the third law, not as a challenge to overcome, but as a truth to accept. The unattainability of absolute zero is not a defeat. It is a covenant, a promise written into the laws of nature that motion will endure, that change will continue, that the universe will never fully fall asleep. And so, in the quiet labs where lasers cradle clouds of rubidium at nanokelvin temperatures, in the cold atom lab orbiting Earth like a frozen jewel, in the superconducting rings of particle accelerators bathed in liquid helium, there is reverence, not worship, but awe. A recognition that we are not masters of nature, but participants in its unfolding. We do not command the quantum world. We listen to it. And what it says, again and again, is this: you may approach, you may observe, but you may not stop. Final stillness is not for us, not for matter, not for time, not for the cosmos itself. Because, in the end, the most unreachable destination in physics is not a place of cold, but of silence. And the universe, in its infinite complexity, has decreed that silence shall never reign, even in the darkest voids, even in the frozen remnants of dead stars, even in the last breath of a dying galaxy. Atoms still whisper, they always will.